Come to the theorem. A bounded function f on closed interval ab is Riemann integrable if and only if it is integrable, in which case the values of integrals every. Come to the proof. Suppose that f is integrable on the closed interval ab. For given epsilon is positive, there exists a real number delta is positive. For so chosen, the upper direction of the function f corresponding with partition p minus lower direction of the function f corresponding to partition p is less than epsilon. That means the difference of upper direction and lower direction is less than epsilon. They are very close for mass of p less than delta. We show the sum s and the integral a to b f. This difference is less than epsilon. For every Riemann sum, the sum is summation k equal to 1 to n f of xk into tk minus 1 associated with a partition p having mass of p less than delta. The lower direction of the function f corresponding to partition p less than equal to the sum is less than equal to upper direction of the function f corresponding to partition p. As the summation, the sum of the areas of the trapeziums lying between lower direction and the upper direction. Since the upper direction is less than lower direction plus epsilon because of this condition, which is less than equal to lower bound of f plus epsilon, which is equal to integration from a to b f plus epsilon, and the lower direction of the function f corresponding to partition p is greater than upper direction of the function f corresponding to partition p minus epsilon from this quantity, which is greater than the upper bound of f minus epsilon equal to integration from a to b f minus epsilon. From these two conditions, we prove that the sum and the integral, they place epsilon. Hence, f is Riemann integrable, and we write r of integration from a to b f is equal to integration from a to b f. It is the assertion, or it is the quantity, find the sum of the trapeziums which have given in date, and as per these conditions we have to show the integral values must agree. Again, suppose that f is Riemann integrable. We consider epsilon is positive, let delta be positive, and r be a number be as given in the definition. We select any partition p with mass of p less than delta, and for each k equal to 1, 2, 3 up to n, because we have taken n number of subintervals, and we select xk any point in the kth subinterval tk minus 1 tk, so that the f of xk, that means the f of xk, f of x k, suppose we have taken this kth position tk minus 1 and here tk, this is the subinterval, this is the subinterval. Here is we have xk taken in the subinterval. My subinterval is look like in this form, or in this form also, in this form also. This f of xk is less than m is infimum of the function f in the closed interval AB plus epsilon. Epsilon is the small increment in this strip. The Riemann in sum S for the choice of x case satisfies the S less than equal to lower direct sum of the function f corresponding to partition P plus epsilon into B minus A. B minus A is the length of the total interval, and its epsilon is the smaller quantity, which implies that the S minus R less than epsilon. S minus R is absolute less than epsilon. The lower bound of the function f, which is greater than lower direct sum of the function f corresponding to function P, is greater than equal to the sum S, the Riemann sum S minus epsilon into B minus A, which is greater than R minus epsilon. S minus R we have taken S minus R less than epsilon, so S is equal to epsilon plus R. So in terms of S we have written R minus epsilon into B minus A. Since epsilon is arbitrary, we have the lower bound of the function f greater than equal to R. By similar argument, it can be shown that the upper bound of the function f less than R. From these two quantities, this and this, since lower bound of the function f less than equal to upper bound of the function f, and the lower bound of the function f equal to upper bound of the function f equal to R. So my integration from A to B f equal to R, which is Riemann integrable, and this integration agrees about my condition.